Okay, good day everyone. Today we shall be looking at the first topic on the AS syllabus, physics, fundamental unit and derived unit. We are going to take it one after the other. After fundamental and derived unit, we will now talk about order of magnitude and estimation. But in this content, we're going to talk about fundamental unit, derived unit, fundamental quantity, derived quantity. I'm going to show you some examples. From there, we go to homogeneity of equations. Then after that, we go to suffix, submultiple, and multiple. So let's quickly look at that now. Now, what are fundamental units in physics? Now, fundamental unit in physics, fundamental unit is also what we call SI base unit. Is also the same thing as SI base unit. Now, where do we get this from? Fundamental unit is also the same thing as base unit, and we got this unit from the fundamental quantity. We have just 7 basic fundamental quantity in physics, just 7. The origin of all quantity are 7. Now, let's list them. Let's look at them. The quantities, like I said, we have just 7 fundamental quantities in physics. Let's see the quantity in tabular form, the unit, and the symbol. Like I said, we have 7 fundamental quantities. One of them is mass. Mass is measured in kilogram, and the symbol for mass is kg. One of them is length. Length is measured in meter, and the symbol is m, small letter m. One of them is electric current. Electric current. The symbol for electric current is amperes. The unit is in amperes, and the symbol is A. One of them is time. Time is measured in seconds. The unit, the symbol is S. And one of them is thermodynamic temperature. Thermodynamic temperature. Thermodynamic temperature is measured in Kelvin, and the symbol is K. 1, 2, 3, 4, 5. Like I said, we have 7 fundamental quantity. The 6th one, maybe amount of substance. The 6th one, amount of substance under quantity. What's the symbol for amount of substance? The unit is measured in mole, M-O-L-E. The symbol is MOL. The last one is luminosity, luminous intensity. That's the last one. The 7th one, luminous intensity. Now, the symbol, the unit for luminous intensity is in candela. The symbol for candela is CD. I'm going to asterisk luminous intensity. It's part of the fundamental quantity, but in the AS syllabus, we are not required to make use of luminous intensity in the AS syllabus. These are the seventh fundamental quantity and the fundamental unit we have in physics. Now, it's from this fundamental unit, we use this fundamental unit to derive or arrive at derived unit. The derived unit are product or division of fundamental unit or quantity. All derived quantity or derived unit are obtained or derived from this seventh fundamental. Whenever you are deriving, you're talking about derived unit. They must reflect all these six or seven fundamental quantity. Now let's see derived quantity and derived unit. Just finish fundamental quantity and the unit. Now let's see derived. Let's see derived quantities and unit. Now, how can we define derived unit? Okay, the base unit are used to derive. Let me give a short note like this and put it down. The base unit. When I talk about the base unit, I mean SI unit or fundamental unit. The base unit or SI unit um, are used to derive all other units. What I mean by all other units, all that I mean derived units are used to derive all other derived units. So the base units are so called because they cannot be expressed in any more fundamental way. So derived units are obtained. Let me put it. Derived units are obtained using operations such as multiplication, and division. These are the two operations we use in deriving derived unit. Now, let's see some derived unit and how we obtain them. I'm also going to put it in tabular form. Quantities, the formula, and derived unit. Now I'm going to start from velocity. Number one, let's take velocity for example. What is the formula for velocity? Displacement over time. Now, displacement is measured in meter, right? Displacement is measured in meter. Time is measured in second. If you notice this meter and second, they are part of fundamental unit. Whatever you are going to use to derive it must be from the fundamental unit. So at the end of the day, velocity is meter per second. Now another one is number two. Let's see acceleration. What is the formula for acceleration? Velocity over time. Now what is the unit of velocity, the one on top? Meter per second. The one down is time. Time is measured in second. This can be written as meter per second times 1 over second. Remember your law of indices? 1 over s is the same thing as s minus 1. Law of indices, remember 1 over a is a raised to the power minus 1. So therefore at the end of the day, acceleration is meter s minus 2. Remember that a minus x multiplied by a minus x. Law of indices is going to give us a minus 2x. That's what I applied there. That's derived unit for acceleration. Let's see another derived unit. We've seen number 3. Let me label it again. Quantities formula and the derived unit. Now we've seen velocity, we've seen acceleration. Let's see force. Another one is force. What is the formula for force? Mass times acceleration. What is the unit for mass? Kilogram. Acceleration is what? Meter per second square. So this is the derived unit for force, kilogram meter per second. Let's see another one. We've seen force, then I can relate it now to maybe pressure. What is the formula for pressure? Force over area. And what is the unit for force? All your units in this topic must be a reflection of the fundamental unit. Don't use Newton at all. Newton is not a fundamental unit. It's not SI based unit. So in this case, force will be expressed as kilogram meter per second square divided by area is measured in meter square. Your law of indices application matters a lot in this case. So this is 1 over meter square, right? Like I said earlier. So 1 over meter square means meter raised to the power minus 2. Or let's do like this to make it easier for us. Let's do like this. From the first one we did, so 1 meter cancel 1 meter. At the end of the day, we have kilogram s minus 2 times 1 over meter, which in turn give us kilogram s minus 2 m minus 1. That is for pressure. Momentum. I'm going to give enough examples so you can apply it when you're solving past paper. What's the formula for momentum? Mass times velocity. The unit for mass, kilogram, velocity, meter per second. Now, let's see energy. Energy or work done. They have the same formula. Energy or work done. That's force times distance. Force, don't forget, force is kilogram, not Newton. It must be expressed as SI based unit. Don't do that mistake writing Newton. Kilogram meter per second square. Distance is measured in meter. So at the end of the day, we have kilogram meter square s minus 2. Now, since we have work done, we can do power now. What is power? Rate of doing work. So the formula for power is work done over time. We got the work done now. Work done is kilogram meter square s minus 2. Time is second. So at the end of the day, when you apply your law of indices, we have kilogram meter square s minus 2 times 1 over s, which is s minus 1. At the end of the day, the unit for power, kilogram meter square s minus 3. That's power. Number 8, let's see charge. Electric charge, Q. The symbol is Q. Electric charge is current times time. Current is measured in amperes, time in second. Let's see more. Let's see more of it. We stop at 8. Let's see 9. Quantities formula and the derived unit. Now, number 9. Okay, let's look at probably potential difference. Let's go complex a bit. Potential difference, electrical potential difference. The symbol is V, that's voltage. What's the formula for voltage? We're going to get there when we start doing electricity. It's one of the seventh or eighth topic in the syllabus, kind of. Now, potential difference, the formula is work done per unit charge. Remember, we just derived work done. Work done is kilogram, that's force times distance, kilogram meter square, S minus 2, that's work done. And charge is current times time, that's ampere second. So this can be written as kilogram meter square S minus 2 times 1 amperes times 1 second. It's the same thing as this. At the end of the day, we have kilogram meter square S minus 2 amperes minus 1 S minus 1. So when you do your mathematics, we have kilogram meter square S minus 3 amperes. This is potential difference. Number 10, let's see electrical resistance. I'm doing enough examples so it will help us when solving past papers. Let's see electrical resistance. Electrical resistance according to Ohm's law. Resistance symbol is R. According to Ohm's law, resistance is voltage over current. That's potential difference over current. What we just derived earlier now is potential difference, which is kilogram meter square S minus 3 amperes raised to power minus 1. Kilogram meter square S minus 3 amperes per minus 1 divided by current. Current is amperes. So at the end of the day, electrical resistance will be when you apply your law of indices, our electrical resistance will be kilogram meter square S minus 3 A minus 1 over A raised power 1, that's A raised power minus 2. Let's see more. Frequency. What's the formula for frequency? F is 1 over period. It's quite easy. That's 1 over second. Of course, S minus 1. So these are the one I've done so far is to give you an insight on how you can get your deriving it. Probably the next chapter I'm going to be solving past papers and all this. That's all for now on fundamental and deriving it. Now let's see homogeneity of equation. Let's see homogeneity of equation. Sorry, I'm trying to take this one to the other side. Homogeneity of equation. Now, what is the meaning of this? What is the meaning of homogeneity of equation? Now, we use homogeneity to balance or to confirm that an equation is mathematically correct. In an equation of physical quantity, the numerical value on each side of the equation must be equal. The dimension must be equal. Once the physical quantity of an equation, the left-hand side, in terms of physical quantity, the left-hand side is the same thing as right-hand side, then we can confirm that the equation is homogeneously correct. Now, for example, what's the formula for area? Length times breadth. Area is measured in meters square. Length is measured in meter. Breadth is in meter. At the end of the day, the left-hand side is equal to the right-hand side. Then this is called homogeneity. This is called homogeneity. So when an equation in terms of physical quantity is mathematically balanced. Left hand side is equal to the right hand side. But it's funny when we are trying to prove an equation with addition or subtraction sign. It's a bit different from this. For example, now the first equation of motion, V equal to U plus AT. Now let's see whether this equation is dimensionally correct. Now, exactly, dimensionally correct. When an equation is dimensionally equal, the left hand side is equal to the right hand side. When the left hand side and the right hand side are balanced dimensionally or in terms of physical quantity, then it's homogeneously correct. Now, like I said, this operation, let me tell you how this one works. Velocity is measured in meter per second. Initial velocity is measured in what? Meter per second. Acceleration is measured in meter per second squared multiplied by time, which is measured in second. At the end of the day, we have meter per second equal to meter per second plus meter. This one is power of 1 minus 2 plus 1 is minus 1. Now, you don't need to add them. This is all what we need. Individually, we have meter per second, meter per second, meter per second. So once we can individually, we can prove the left hand side. The left hand side physical quantity is equal to individual. Is the same thing even on the right hand side. Then it's correct. You don't need to add them. This works for both addition and subtraction. Let's see another one again. Let's see another one. Okay, let's see v squared equal to u squared plus 2as. Let's see if it's dimensionally correct. Velocity is measured in meter per second. It has a power of 2 now. Don't forget to put it. Initial velocity is measured in meter per second. It has a power of 2. Don't forget to put it. 2 is a constant. It has no dimension. We don't need it here. Numbers, they are constant. They don't have dimension. They have no unit. So we don't need them in this context. Acceleration is meter per second squared. Distance is measured in meter. So from here we have meter squared s minus 2. When you use the operation of power of 2, meter squared s minus 2 plus this one too, we have meter times meter squared s minus 2. You can see the left hand side is the same thing as individual, so it's dimensionally correct. Now let's see another one. This is dimensionally correct. Let's see another one. Okay. Okay. Use is a question. Use the base unit. Okay. Let me take it to the other side so you can do it on a fresh page. Another example. The question is use the base unit. This question is I got this question in one of the textbooks. The Cambridge recommended textbook. Use the base unit to show that the equation below is homogeneous. Now the equation is work done. The equation is work done equal to gain in kinetic energy plus gain in potential energy. Now we have to use this equation to show that the equation is homogeneous. Okay, quite simple. Work done is force times distance kinetic energy is half mv squared. At the end of the day, its potential energy is mgh. Now, force is kilogram meter per second squared. Distance is in meter. Number has no dimension, take it out. Mass is kilogram. Velocity is meter per second. You know it has a square, don't forget to put it. Mass is kilogram. G is gravity, meter per second square. Height is like length, meter. At the end of the day, we have here kilogram meter square s minus 2. Here we have kilogram meter square s minus 2. And also here we have kilogram meter square x minus 2. Yes, this side, this side, this side are the same. So the equation is homogeneous. Let me solve one question on quantity. Now, given that, another example. Now, given that this is the formula for drag force is equal to half c density A v square, where F is drag force, and this is density. A equal to area. They will tell you the meaning of the individual quantity, so you know the formula to use. V is velocity. The question is show that C has no unit. Show that C has no unit. Okay. Since you are looking for C, let's make C the subject of the formula. When you are dealing with unit of physical quantity, number has no business there. Take away the number. So at the end of the day, we have F equal to C density area V square. Make C the subject of the formula. That is what we are looking for. That will be force over density area V square. We have to show that C has no unit. Force. Of course, what unit of force? Force is MA, kilogram meter per second square. Density is mass over volume, right? We know density is mass over volume. That's kilogram per meter cube. Area is meter square. Velocity is meter per second. You know, in the formula it has square. At the end of the day, we have C equal kilogram meter per second square all over kilogram meter cube times meter square s minus 2. Okay, now kilogram cancel kilogram. At the end of the day, now with 1m cancel 1m here. At the end of the day, we have s minus 2 on top. Down, this is m minus 3 is here. This is m times m squared, that's m cubed, and this is s minus 2. S minus 2 cancel s minus 2. M minus 3 times m is about 3. That's m minus 3 plus 3. That's m0, that gives us 1. So at the end of the day, this one is out. So no unit. 1 is not a unit. Don't write 1. Just say, since all the units that's cancelled out, just say no unit. That's the proof. That's it. So I believe it's clear. Let's move to the next one. Let's see the submultiple, multiples, prefix. Let's see how to use them. Okay, now let's say in physics what we call multiples, submultiple, and prefix. Let's see what we call it. Now in physics, multiple are generally multiple are number with positive power. Multiple, when you think about multiples, just think about positive power. So multiple, negative power. Now, how and when do we use them? Generally in physics, when we have very large number, we take them to standard form using multiple. And when we have multiple, very large number, now turn it to standard form. So multiple, very small number. So multiple of a very small number. Now, let's see the fixed one. Multiple, we have some constant multiple we use a lot in physics. The prefix and the symbol. Let's see that now. Now, like number 1, 10 raised to power 1 is called deca. It's called deca. The symbol for deca is dA, small letter dA. 2, number 2, 10 raised to power 2. 10 raised to power 2 is called hector. The symbol for hector is small letter h. Number 3, 10 raised to power 3, you're familiar with that. That's kilo. Capital letter K. That's kilo. Number 4, let's see, maybe 10 raised to power 6, you're also familiar with that. The one you call gigabyte, giga, capital letter G. Number 5, maybe 10 raised to power 15. These are the common ones we use in physics. So 10 raised to power 15 is peta. The symbol for peta is capital letter P. Number 6, 10 raised to power 18, that's exa. The symbol is capital letter E. Number 7, 10 raised to power 21. 10 raised to power 21 is called zeta. The symbol is Z. And let's see if there's space. Oh, there's still space. Number 8, I've done 21. Okay. Oh, no. The 10 raised to power 6 is not giga. It's mega. Sorry. 10 raised to power 6 is mega. Sorry, it's not giga. 10 raised to power 6 is megabyte. The symbol is capital letter M. Okay, I've omitted 10 raised to power 9. That's the one they call gigabyte. 10 raised to power 9. The symbol is G, capital letter G. Number 9, I've done 21. Oh, I've missed. Okay, 10 raised to power 12 too is common. That's terabyte. Tera. The symbol is capital letter T. Number 10, 10 raised to power 24. That's yokta. Okay, there's no space. 10 raised to power 24 is yokta. The symbol for yokta is capital letter Y. So these are the most common multiple we use in physics. The multiple, the prefix, and the symbol. And let's see submultiple. Let's see the submultiple. Submultiple, the negative power, like I said earlier. Submultiple, negative power, the prefix, and the symbol. Now, what are the submultiple we have? 10 raised to power negative 1, the one you call deci. The symbol is small letter D. 10 raised to power minus 2, the one you call centimeter. The symbol is small letter C. 10 raised to the power minus 3. The one you call millimeter. That's M, small letter M. 10 raised to the power minus 6. The one you call micro. We use this one a lot in capacitor. The symbol is this, micro. 10 raised to the power minus 9. That's nano. Symbol is N. 10 raised to the power minus 12. That's pico. The symbol is P. 10 raised to the power minus 15. That's femto. They're all small letter. The symbols are small letter F. They're all small letter. Femto, small letter. 10 raised to the power minus 18. This is atto. Small letter A. But again, 10 raised to the power minus 21 is there. That's zepto. The symbol is small letter Z. And the last but not the least, 10 raised to the power minus 24. That's yocto. Small letter 1. Now these are the multiple and sub-multiple we use in physics. So my next class will be on order of magnitudes, which is coming shortly. See you soon.